Welcome to Pre-Calculus, another lesson on limits here. In this video, we're going to be talking about limits and continuity. So we really have, I hope by now, we have a good understanding of limits and one-sided limits. And now, because of that good understanding, we can really talk about continuity. We did briefly explore continuity in the past, but now we can do it really a lot better. So before we just kind of mention that a function is continuous at a value x equals a, if the function that kind of like goes through x equals a with no issues. So we just kind of said there was no issues, and we talked about some issues, but let's better define that. So this graph does a great job of showing how as the function f of x passes through x equals a, nothing happens. This means the function is continuous at x equals a. But let's really talk about why here. So if we look at this graph, the first thing we can notice is that there's no issues. Now, what do I mean by issues? Well, there's several issues that we're going to talk about here shortly, but we have vertical asymptotes and holes are kind of like the big ones, and jumps as well. But if we look at this, what happens at f of a? Well, there's clearly a point. I mean, I clearly see a point. I don't see a hole. I don't see an asymptote. I clearly see a point. And that point looks to be at about, I don't know, if we count up here, 1, 2, 3, 4, maybe somewhere around 4.5. So when we plug a into this function, we get 4.5, okay? Now that's awesome. That's great. That means there's a point there. But again, nothing happens there. It's nice and continuous. If I'm going to draw, I don't have to lift up my pencil. I could draw right through a without having to lift up my pencil, which is awesome. So that's a good idea of what continuity looks like, or what it means to be continuous. All right, so what are some types of discontinuities, places where you're not continuous? Well, if you remember, we talked about this one. This is called a removable discontinuity, which is really just a fancy way of saying there's a hole, but removable is like the more sophisticated way of saying it. So obviously, in both of these graphs, we see the issue where at a, we see this kind of gaping hole. Now, these two graphs are slightly different. The one on the left is what I call displaced point. So there is a point at a, so f of a is defined, but it's just not where the two sides come together for the limit. Which is going to be really important when it comes to continuity. And then on the second graph over here on the right-hand side, once again, the f of a is completely undefined. There is no point at f of a. So either way, these are both what we would consider removable discontinuities, right? The function is clearly not continuous. So in this left graph, I'm going to draw this function. I have to lift up my pencil, come down here, fill in this point, put my pencil back down and continue drawing. And then even on this one with a hole where it's completely undefined at a, I'm just going to have to lift up my pencil and then continue on the other side. So that's not continuous. Those are removable discontinuities. Then we also talked about a jump discontinuity. A jump discontinuity is where basically the two sides don't match up. So what happens at A? Listen, there could be a filled in dot at A, or both of the ends could be open. It doesn't really matter. What matters is that the left side and the right side are not coming together. So if I have to draw this, I'm drawing this, I have to lift up my pencil to come over here and finish the drawing. So it's clearly not continuous, but that's an example of a jump discontinuity. And then finally, we have infinite discontinuities. These are happen at VAs, which I call vertical asymptotes. So vertical asymptotes create these infinite discontinuities. So we see three examples here. So here we have a vertical asymptote of 2, and both sides are going up forever. Now, even though they're both going up forever and it may look like they're kind of getting closer to each other, they're really not. They're just continuing on this upward trajectory, never ever stopping as they go towards infinity. The second one here in the middle, there's another vertical asymptote at x equals 2. This time the left side is going towards negative infinity, the right side is going towards positive infinity, and clearly nothing is defined at 2. So in both of these first two graphs, there's nothing defined at 2. So f of 2 is completely undefined. Now, this is a really weird graph, this far right one here. This is going to be probably some type of piecewise function. But what's important is that couple things. So first off, there is a point. So we are defined at x equals 2. We see that point right here. But the right side is obviously going towards some type of asymptote. Even though the left side is approaching 1, that's this value right here, we clearly see that the left-hand side, is approaching 1, but the right-hand side is going up towards infinity. So basically, if both or one of your sides is approaching infinity or negative infinity, that's going to create an infinite discontinuity. So how does this connect to limits? Well, when we look at these situations, we kind of just said, hey, continuous means that you're nice and smooth and you can draw it without lifting up your pencil. And then, we clearly understand a removable, a jump, and an infinite discontinuity, but we really want to be able to define these things very, very specifically so we know exactly what's happening. And we could do that with limits. So here is a much better way to define continuity with limits. So this is what it means for a limit, this is what it means to be continuous at x equals a. So there are three things that kind of have to be checked off as you are checking for continuity. The first thing is that the function must be defined at a, which means that there has to be a point at x equals a. So when you plug a into the function, you need to get something out. You have to be getting a number out. 0 counts as well. Please don't forget that. 0 is a number. So we have to be defined when we plug a into the function. And again, what does that mean graphically? It means there's a point there. Now, the second thing is that the limit must exist as we approach a for this function. So if you kind of put our dotted line at a, so as the left side comes in and the right side comes in, they have to be created. There can't be an asymptote there because that's going to be a limit that does not exist. And there cannot be a jump because a jump, the two sides don't come together. So their two sides have to come together, which allows for the limit to exist. So this means there has to be a limit. And the final thing that has to be true is that the previous two answers, where the function is defined, where that point is at, is equal to the limit as x approaches a. These two things have to be equal. And this is actually really important because if there is a hole right here, then the limit does exist. Remember, the limit does exist as you approach a hole, but you're not defined because there's a hole. So that's why it's super important that not only does 1 have to be true, not only does 2 have to be true, but they have to be the same number, showing that the point is where the limit comes together, which makes it nice and smooth and continuous. So when you're checking if you are continuous or not, all three things have to be checked. If any one of these three things fails, well, sorry, you're not continuous. So I always recommend starting at 1, then 2, then 3, going in this nice order. And if 1 fails, then you can just stop right there. There's no point in going on. So for example, that's a vertical asymptote. If there is no point, it's not even defined at x equals a, then you probably have a vertical asymptote. Now, there's some other things that could happen, but most likely it's a vertical asymptote. So just stop right there. You're obviously not continuous. So let's actually practice that. So here's that graph that kind of has a lot going on in it. And if we look at this graph, we see an awful lot. But the first question is, check if the graph is continuous at x equals -1. So I'm going to go through my checklist. So first thing I'm going to check is, does the graph exist? Does the function exist at -1? And I don't see any hole, I don't see any jump, I don't see any discontinuity. So I clearly see a point right here, and it looks like that point is at +0.5. So +0.5 would be a good approximation for that value. Okay, next question is, does the limit exist as x approaches -1 for this function? And I recommend drawing that dotted line at -1 and saying, okay, left side is going there, right side's going here. Oh my gosh, the two sides are coming together, and it looks like the two sides are coming together at 0.5. This is awesome. So far, so good. And then the third thing I have to check is that the previous two answers are the same. 0.5 does in fact equal 0.5. So check, check, check. Yes, we are continuous at -1. So again, if I erase, you can clearly see that as we draw our line through -1, we have no issues whatsoever. So I know most kids will say, well, if I could just tell that in the graph, why do I have to check these three things? Well, sorry, that's just a definition. We do have to check these three things. All right, let's check the next one here. Are we continuous at x equals 3? So the first thing I'm going to figure out is the graph defined? Is the function defined at 3? And yeah, it is, right? There is a solid filled in dot at 4. So the function is definitely defined at 3. It's a solid dot there. Next question is the limit, or what is the limit as x approaches 3 of this function? And that's where I maybe draw that dotted line. And I'd say, okay, left side, right side are coming together. Looks like they're coming together at maybe 1.2-ish. So yes, the limit does exist. The two sides are definitely coming together as we approach 3. We love that. The limit does exist around 1.2. So far, so good. But when we go ahead and say, does 4 equal 1.2? Absolutely not. that confirms that, sorry, we are not continuous at 3. And again, if I erase all this, it's pretty obvious, right? It's pretty obvious that there's a removable discontinuity at 3, hence I'm not continuous there. But this allows us to do the official checking of that. All right, let's do -4. All right, so first off, we're going to say, is the function defined at -4? And yes, it is. I see a solid filled in dot right here at 2. So it's definitely defined there. And then we'd say, well, does the limit exist as x approaches -4 for this function? And we'd say, okay, well, the left side is down here at -2. The right side's up here at +2. So sorry, the two sides are not coming together. The limit does not exist. That's clearly a jump discontinuity. Now, since the limit doesn't exist, I could stop right there. But if you want to continue on and say, okay, does 2 equal dne? Well, obviously not, right? Come on, it doesn't happen. It does not work that way. So we clearly have a discontinuity there. And again, we see that in the graph. Like, you don't really need to check these 3 things with the graph, but I'm going to require you to do so because it's important to understand the 3 ideas. All right, there's one more place I want to check that I actually didn't write here, but that is at -2. And x equals -2, am I continuous? So the first thing I'm going to do is determine, is there a point? Does the function exist? Is it defined at -2? And as I draw that dotted line, I don't see any dots there. I don't see any points. So it looks like it is undefined. And that's pretty obvious, right? There's an asymptote there. So we say, well, what's the limit as x approaches -2? Now, technically, I don't have to be doing this because once I find out that there's no point at -2, then there can't be continuous. But I'm going to continue on anyway. What's the limit as x approaches -2? Well, the left side's going up forever. The right side's going down forever. The limit does not exist. And then finally, again, even though I don't need to do this, the limit doesn't exist. The point doesn't exist. I mean, I'm pretty sure it's not continuous. But lastly, undefined does not equal does not exist. These are not 2 values that could be equal. So it just doesn't work that way. So sorry, we're clearly not continuous at -2. So I literally went through all 4 different things that can happen. We could be continuous. We could have a hole. We could have a vertical asymptote, or we could have a jump. Now, a cool way to kind of walk through this, right? So I kind of followed the 3 rules, but there's a different way we can walk through this, and Delta Math kind of does it this way, which I think is pretty cool. So it's kind of like a going through all the different things and kind of filling stuff in. So here is this graph. It's the same graph we're just looking at, but notice how I have a bunch of boxes that have to be filled in here. And I think these problems are actually kind of fun because they really allow us to explore what's happening. So this problem is exploring 2. So we're exploring what's happening at x equals 2. All right, so the first thing that says, what is the limit as we approach 2 from the left? We see a little minus sign here from the left. So I'm going to go and put my dotted line at 2. As I approach 2 from the left, I would say I'm around, 1.2. Excuse me. All right, what about as we approach 2 from the right? All right, looks like from the right-hand side, looks like I'm also at about 1.2. All right, well, it can be then determined that the limit does exist because the left side and the right side are coming together. This means that the limit does exist, and it exists at 1.2. Okay, right? If the 2 sides are coming together at 1.2, then the overall limit does exist at 1.2. This is awesome. But furthermore, I can also determine that at f of 2, the function is defined. And again, let me erase my work here so we can actually see that the function is defined at 2. I don't have any issues there. So there's clearly a dot. There is a point at 1.2. And then now, because the limit is at 1.2 and the point exists at 1.2, then we can clearly say that at x equals 2, the function is continuous. And again, why is it continuous? Well, it's continuous because f of 2 equals the limit as x approaches 2 for this function. That's really the final nail in the coffin that allows us to say we definitely are continuous here. All right, this time let's look at -2. Now, we already kind of talked about -2 before. We're just going to look at it again through this kind of different perspective here. But we'd say, all right, what happens as we approach -2? Go ahead and draw that dotted line at -2 if you need to. What happens as we approach -2 from the left-hand side? So that little minus sign there. So left-hand side looks like we're going straight up towards infinity. What about from the right-hand side? Well, it looks like we're going straight down towards -infinity. So it can be determined that the limit as we approach x equals -2 does not, sorry, put the end first, does not exist. So there's no value, right? There's no value for me to exist at. The limit does not exist because the 2 sides are not coming together. Now, I can also continue on to see that at -2, the function is also undefined. Nothing happens at -2. Well, that's a bummer. That clearly means that we are discontinuous. And this is an infinite discontinuity, which is pretty obvious because the two sides are going towards infinity. And again, this is happening, well, for two reasons, right? First off, the point is undefined, and the limit does not exist. So kind of two reasons why that we are completely discontinuous at that value of -2. All right, let's do a third example here. This time we're going to explore x equals 1. All right, so once again, draw that dotted line if you need to. All right, what happens is we approach 1 from the left-hand side. Left-hand side looks like we're at maybe 1.1, somewhere around there. What about from the right-hand side? Well, also looks like we're maybe around 1.1. And since the two sides are coming together, that means that the limit does exist. And it exists at 1.1, which is awesome. All right, then we're going to say, okay, well, is the function defined at 1? If I plug 1 into the function, do I get a point? And that's where I'm like, oh boy, no, there's a hole there. We're undefined there, UND for undefined. So therefore, because the limit exists, but the point's undefined, sorry, we are discontinuous at x equals 1. And again, we're discontinuous because f of 1 does not equal the limit as x approaches 1. So the limit does exist at 1.1, but f of 1 just does not exist. That's why, sorry, we are not continuous. Or we are discontinuous. All right, let's look at one more example. I know this is going to get boring, but it's important to go over them. All right, this time we're going to explore -4. So again, draw that dotted line if you need to. All right, what happens is we explore -4 from the left. As we approach -4 from the left, we're down here at -2. As we approach -4 from the right, we're up here at +2. Well, wait a minute. The limit cannot exist. There's just nothing there because the two sides are not coming together. That's a jump discontinuity. Now, it's important to note that the function is defined at -4. There is a point at 2, but sorry, therefore, we are discontinuous at x equals -4. It's a jump discontinuity. Again, why? Well, because the limit did not exist. The limit as x approached -4 did not exist. And again, the point existed, right? But sorry, the limit did not exist. And that's the important thing that I'm trying to emphasize here is to be continuous. All three things have to happen. You have to have a point that's defined at that value. The limit has to exist as you approach that value. And the most important thing is that those two things are equal. If none of that happens, sorry, we don't exist. Now let's talk a little bit more about jumps because sometimes jumps can confuse kids a little bit. The one thing I want to make sure that I mention is that the potential for a jump occurs usually only in piecewise functions. Not always, but in our cases, most of the times if we are going to see a jump, it's going to happen in a piecewise function. So I really want to make sure you guys understand that the jump will potentially happen where the two pieces come together. So where we are pieced together. So to me, like a piecewise function is like Frankenstein. We can take a piece here and a piece of this and a piece of that, a piece of this. We put them all together and we hope it looks pretty. Well, if there is a jump, it's going to happen where we piece the two functions together, which is going to happen at 3. So my recommendation is to plug 3 into both functions. And if they come together, well, then you clearly don't have a jump. But if they do come together, then there is no jump. So that's what I'm going to recommend we do here. So we're going to plug 3. And again, it's important that you recognize that 3, again, is where they come together. That's where the jump has potential. So we're going to plug 3 in, 5 minus 3 squared. That's going to be 5 minus 9. 5 minus 9 is -4. So that's going to be on the left-hand side, less than 3. On the right-hand side, we have 2 times 3 squared minus 8. Let's see here. 3 squared is 9. 2 times 9 is 18. 18 minus 8 is 10. So clearly the two sides are not coming together. So there's definitely a jump here. So there's definitely going to be a jump discontinuity here. And again, it's because the two sides are not coming together. So where we stitched or sewn these two functions together was not lining up at all. One side was at -4, one side was at 10. On this second example, the potential for a jump happens at -1, again, where they're pieced together. So we're going to go ahead and just plug in -1 to both sides. So we have 3 times -1. By the way, I forgot to mention, if you have a jump, you're obviously not continuous. You should have known that. But anyway, come back over here. 3 times -1 minus -1 squared. Be very careful. Don't make those two negatives into a positive because you got to do the squaring first. So 3 times -1 is -3 minus 1. Again, -1 squared is 1, and then so -1 is -1. Again, you cannot make those two negatives a positive because that square needs to be done first. So -3 minus 1 is -4. Okay, great. Then we have x squared, which is going to be -1 squared minus 5. -1 squared is 1. 1 minus 5 is -4. So this one will not have a jump. So no jump here. So this could be continuous because there's no jump. The two sides come together at -4. So we stitched these two functions together perfectly at -4 so that there'd be no problems. Another type of problem that we see very popular, in fact, we've already seen this problem a couple weeks ago, but it's a piecewise function where we want to make the two sides come together. So once again, the two sides are going to potentially come together at 5. And we want to force them to be together. So the problem is saying, hey, what does k have to be? And k is this value right here. What does k have to be that will force these two functions to come together? So first off, remember, to be continuous, the two sides have to come together. So that means that these two functions have to be equal, because that's what it means to come together, is that they are equal. And then the whole point is, okay, what's the x value where they're coming together? Well, again, that's 5, right? That's where we're sewing these two functions together, is at 5. So that means the x's are going to turn into 5s. And then all we really have to do is solve for k. I mean, these problems are unbelievably easy if you understand them. So we get 10k plus 16 equals k minus 20. Let's see, I'm going to subtract the k over to get 9k. I'm going to subtract the 16 over to get -36. Divide both sides by 9, I get k equals -4. So if k equals -4, then these two functions will come together at 5. So if 5 gets plugged in, as long as k is -4, then the two functions will come together and hopefully be continuous. So again, hopefully you understand this video. It's all about trying to connect what we've already learned about continuity, but really try to define these values and understand all these different issues through limits. So here is the beautiful example that we have continuity. This is where the function exists exactly where the limit exists. They're both the same. Removable discontinuities, your limit might be different than where your point is. And that's going to, again, if those don't match up, that violates number 3. Or again, on the second graph here, the limit does exist, but nothing exists at A. So again, that's going to be a removable discontinuity. Here's that jump discontinuity where maybe you do exist at A. We do see a filled in dot here at A, but the limit does not exist because the two sides don't come together. And then we also have those infinite discontinuities where it's kind of like a double whammy. Typically with a vertical asymptote, the point, there is no point. The function is undefined at 2, and the limit does not exist. Well, if that's happening, then you clearly are not continuous. So again, these are the 3 things that truly have to be checked one at a time. And if any one of them stumbles and fails to be true, then sorry, you're not continuous. So this is really just an extension, right? This little lesson today is really more about continuity, but to help us better understand continuity, we can utilize limits, which is why learning limits is super important. All right, guys, that's it for this video on continuity and limits.